plus V1. Okay, 4 plus V1 is just V2. V2 is 4 plus V1. Okay? Minus this voltage drop. So this part over here is just V2. 4 plus V1 is V2. And that is the voltage drop, or voltage at that point. And as the current flows, the voltage is going to drop to a lower value. So V3 is that value minus Ix times 3. Okay, that Ix times 3 has nothing to do with this other voltage source created by this current over here. This is just from the fact that over this loop it has to satisfy this law. Okay, so this branch over here is by writing the voltage relationship over here. Okay, and as I said before, V2 minus V3 is Ix times 3 because of the Ohm's law that this resistor has to satisfy. Okay? And as a result of that, I get this equation, which is V3 minus V2 must be Ix over 3. And then if I shift this and replace V3 minus, let me see, V2, right? This part is V2. V3 minus V2 must be equal to that. And then if I shift that over, and if I look at this equation in terms of V1 alone, okay, I get that equation over there because V3 is also equal to 3Ix. I can replace this equation being equal to 3Ix because V3 is also equal to 3Ix. Okay. Now, if I solve for Ix then, okay, let me see, V1, V3 is also equal to 3Ix. That's why I can write this equation in this manner. I can directly go to here if I want to. I can directly go from this equation to this equation if I want to. Or I can go through this equation first and get there. And then I solve Ix to be V1 plus 4 over 6. So once Ix is found, I will find my V1, and once my V1 is found, I can find my V2, and once my Ix is found, I can also find my V3, and this problem is solved. Once V1, V2, and V3 are solved for. Okay, it's rather complicated, yes?
We seem to be solving the problem without using the 4 ohms.
Oh, why do you think so? Why is 4 ohm not involved? You might puzzle a little bit. Why is 4 ohm not involved? It's a strange phenomenon, right? It's good that you point that out. Why is 4 ohms not involved? I can put 5 ohms there. The answer would be the same. I can put 6 ohms there. The answer would be the same. Why is 4 ohms not involved in this problem?
You're calculating the current and the thing over there and not the one for the 4 ohm resistor.
Because this current, this is a very strange circuit because this current controls the voltage drop here. Okay, once this current controls the voltage drop, it doesn't matter what Iy is. Okay, it doesn't matter what Iy is. Okay, it will have Iy flowing in such a way that this voltage drop is always 3Ix. Okay, you will have to have 4 times Iy equal to 3 times Ix in order for this problem to be satisfied. So you change your 4 ohms to something else, your Iy will just change to adjust for that. Okay, it will just change to adjust for that. So this is a strange circuit in that sense, that the other parts of the answer does not depend on this 4 ohms. You change it to 5 ohms, you just change Iy. You don't change any of the other values. Yes, you have a question?
When it's all said and done, you know what Ix is supposed to be?
Ix is equal to here, right?
Right, so once you have a numerical value for it, just try and check my answer.
I can solve for V1 first. Okay, from this equation I can solve for V1. And if I solve for V1, I have V1 is equal to 6V1 is equal to minus V1 minus 4. Right? If I get my algebra correct. And then 7V1 is equal to minus 4. So V1 is minus 4 over 7. if I get my algebra correct. And then you plug this in here, you get your Ix, and then you work backward, okay?
Thank you.
Yeah. Any other questions? Okay, seems that all of you are getting it, so you should have a lot of fun with the homework. Okay. So work on the number of equations so that you have the number of equations to solve for the number of unknowns. And you notice that not always KCL is being invoked. Sometimes you have to invoke KVL. Okay, if you don't find the number of equations that you need, think about KVL as well. So some of these equations are not solved or invoked or arrived at just by using KCL. Only the very simple case, you do KCL. Okay, let's try another method. We have the node current method. Well, the natural thing then is that you have the loop current method. So in this method, you try to draw loops in order to solve the problem. And that after you draw the loops, you apply KVL. Okay, so this method was applied in conjunction with KCL, but this method is applied in conjunction with KVL. So let's do a very simple example. A 3-volt source over here, a resistor over here, and a voltage control voltage source, 4Vx. Okay? And then you have a 2 volts over here. This is a very simple problem, and you can do that with one loop. And this voltage is called Vx. Okay, you need to only draw one loop to solve this problem. This is loop current method. And then you apply KVL to this loop. If you apply KVL to this loop, you must have 3 volts must be equal to 2 times I. Okay, I being the current flowing in this loop. Okay, I can put I here as well. It's the current that is flowing around this loop. Okay, I call that I. 2 times I. And then plus 4 times Vx. Okay, there's a voltage drop over here. This voltage is higher than this voltage. So it's 4Vx. And then plus 2 volts. This is just KVL. 3 volts must be equal to this voltage plus this voltage plus that voltage. Okay. But we know what Vx is. Vx is equal to I times 2 ohms. Okay? So we can also replace it with 2I plus 4 times 2I. That's Vx plus 2. So this equation can be written as such, and then you can solve for your I. So very simple example. The loop current method. Let's do something that is slightly more complicated than this. Do you have any question regarding this? Find the current loop, define the current loop, and then apply KVL. Okay? So do a slightly more complicated example. I have a voltage control, not voltage control, independent voltage source, a resistor here, and then minus 2 volts. Okay, and you know what this means. Minus 2 volts means that this actually is lower in this voltage. This is 1 ohm, this is 2 ohms, This is 3 ohms. Okay, and this is I1. This is I2. Okay, so let me see if I get those numbers correct. Okay, so these are the numbers that we have in the textbook. And this is I1. If this is I1, it means that this is I1. This also is I1. Okay? And then this is also I1. This is what this diagram means. If this is I2, it means that this is I2. This is I2, and this is I2, and this is I2. And over this branch over here, okay, over this branch over here, it is I1 minus I2. Okay, so both kinds of currents flow on this common branch. This is a common branch to both the loops. So this current should be I1 minus I2. Okay? So, in fact, you can see that Kirchhoff current law is automatically satisfied at that node over there. Then you write the Kirchhoff voltage law now. Kirchhoff voltage law says that Ix, okay, let's call this current Ix. Okay, Ix is I1 minus I2. That's what the textbook calls, and it's just that current that's flowing down that branch over there because there's a common branch between the two loops. And then we apply Kirchhoff voltage law to one of the loops. Okay, let's say that we apply it to that I1 loop. 5 volts must be equal to I2 times 2. Okay, I2 times I1 times 2, sorry. I1 times 2 plus 1, the resistor in this branch times I1 minus I2. Okay, so this is 1 KVL equation that we get out of that loop. And then we apply KVL to the other loop. Okay, it says that this voltage drop across this resistor, which is 1 times I1 minus I2, okay, must be equal to 3I2, because this current that flows through that resistor is I2, so the voltage drop across that must be equal to 3I2, okay, minus 2 volts, plus minus 2 volts. This is a voltage drop across here. This is higher potential than here. This potential drop must be equal to this potential drop plus this potential drop, which is given by this equation. So you have two equations, two unknowns, and you can solve for them. Okay, this is the current loop, or loop current method. Okay, I have 2 minutes left. Instead of starting a new example, why don't you ask me as many questions as you like before the bell rings regarding the loop current method as well as the loop current method. Yeah.
Are there certain times where you use the certain one, or is it just one people use one or the other, depending on the problem?
Some problems are more easily solved using the second method. Some problems are more easily solved using the first method. Both methods are equivalent to each other.
So you could solve any survey with the other just
One or the other. I would prefer method 1. Okay, I would prefer method 1 over method 2. Okay, because method 2 you have to find the loops. And you have to count the number of independent loops. This loop is not counted as an independent loop. You have this loop over here, big loop. It's actually dependent on this smaller loop. So that big loop is not counted as a loop. Okay, and you have to figure out how to do that. Some loops are independent of each other, and to the beginner you might not be sure what loops are independent of each other, whether you're using redundant loops or not. Okay, but in the beginning, you know that all the small loops are independent of each other.